Hi guys, Buildzoid here, and today we're going to be doing a PCB breakdown of the RTX 2070 Super Gaming X from MSI. So the pictures are from Tech Power Up, so huge thanks to them for providing high-res PCB pictures in their reviews. There's going to be a link to their review of this card down in the description below. With that out of the way, let's get back to the card. One thing worth noting is that MSI has used this PCB in the past on the RTX 2070. And for some reason, I don't have a PCB breakdown of that one, so we're doing it now with this one, because, yeah, I thought I covered every single 20 series card there is, but apparently I didn't. Well, most of the interesting 20 series cards. There's some that were just like, as far as I'm concerned, and so I didn't look at those, but, yeah, anyway, so let's get into this one. So this is on the 2070, it was actually the Gaming Z, but now it's like the Gaming X that uses this PCB, but anyway, let's get into it. Starting off with by far the most important section of the card, or at least in my opinion, most important section. Like, the thing is, even if, say, like this one of these two regulators down here, which one of these is going to be like 1.8 volts, which you need for your memory chips and your BIOS, and one of them is going to be the PEX rail, which you need for your PCIe interface. Well, like, neither of these provides a substantial amount of power. But if one of them stops working, the whole card stops working, right? Like that's one of the, like that's the thing that I absolutely hate about, like, people sending me questions about troubleshooting is like, my card doesn't put out an image, and it's just like, well, basically anything on the GPU being broken would lead to a black screen if you think about it for long enough, right? Like, literally any vaguely more serious malfunction is probably going to prevent the thing from initializing. So, yeah, that is not helpful information. Anyway, so those two minor voltage regulators exist. There should also be a 5 volts rail somewhere on this card. I'd have it as a guess that it's in this area, just because there isn't really anything. Well, it could also be like that inductor over there, but yeah, I'd guess it's over here. Anyway, there is a 5 volt regulator somewhere on the card because these are 5 volt driver chips. But back to the VCore VRM. The VCore is a 1, 2, 3, 4, 5, 6, 7, 8 phase. We have these lovely inductors. I'm actually kind of a fan of these. Like, they do look kind of silly, but at the same time, like, we've all seen what I'm willing to do to my own GPUs. So it's like, this is totally up my alley. In fact, I'm kind of sad that they didn't opt to go for like if they just used straight up like bog standard off the shelf Nichicons, all of these capacitors would have had red labels. I'm kind of sad, like, and then it would have color coordinated with the inductors, and I think that would have looked a bit better. But as it is, I actually have no idea who makes these. They do seem to be rated for 5,000 hours, so that's decent, and they're aluminum polymers, so you know, they're not that concerning. It's not like your typical liquid electrolyte capacitors where if you overload them for, like, if they run too hot for long enough, they might just blow up and that kind of thing. Whereas aluminum polymers will actually, like, when the lifespan rating on aluminum polymers isn't so much when they fail completely, but it's like when they start being slightly less good at doing their job than normal. So, you know, even after exceeding the lifespan of an aluminum polymer, you might find it still works perfectly fine. So, yeah, anyway, we do have 8 phases worth of VCore. That is provided by this lovely, or more like controlled by this lovely chip right here, which is, of course, the UP9512, which is the standard for the sort of, like, lower cost 20 series cards. Like, if you have a really high-end RTX 20 series card, you're probably going to see an MP2888, which is a 10-phase controller from Monolithic Power Systems. That thing is crazy expensive and is quite special. But for a lot of the other cards, like for more normal cards, you'll see the UP9512. There's also one other chip that, like, Galax uses for their Hall of Fame, which is some IR thing that I've forgotten the part number of because it's on one card, and, well, that's why I don't remember it. Yeah, for most other cards, you're normally going to see a UP9512. And the thing about the UP9512 is this is basically an upgraded version of the old UP9511. It offers the same number of phases, so 8 phases, 2 megahertz switching frequency, which is actually a significant increase in switching frequency because the 9511 only went up to 600 kilohertz. And much more importantly, not only does it have PWM vid, it also has I2C or I2C, which I've written it as I2C, so you know. Anyway, so it does have an actual digital interface. The 9511, completely analog. Everything about that chip was configured with resistors. There was no way to get any kind of like monitoring out of that chip because like it doesn't understand, like it's not digital. It won't tell you what the temperature of the VRM is because there's no way to do that. But with the 9512, yeah, there are some digital control options. It's not like, I don't think it goes as far as most of the other international, like proper high-end digital controllers. I didn't really bother to look into the the functionality in the datasheet too much because for the most part, this thing is still like yes, you could mess around with trying to control it over I2C. You can still totally configure the whole thing with just resistors. So yeah, and if you did want to mess around with I2C, well, on this card you have this very convenient connector right here labeled for you. So that should make life quite easy. If you want to, you know, try mess around with software control on this, which actually I think the Elmore EVC might have support for this chip. But anyway, so it is an 8-phase. It's somewhat, you know, digitally controllable, and it goes up to 2 megahertz switching frequency. So that's all I really care about with the controller, and it's made by UPI Semiconductor, which you would know because it has a UP part number. So anyway, let's move on to the actual VCore VRM itself. So each phase, we have one inductor, 2 sets of dual NFETs, and then 1 driver. The drivers are UP 1965, nope, that's not a 1965 Ps. These are 5-volt drivers, so yeah, that's what those are. And then the dual NFETs are Fairchild Semiconductor FDPC the 5018 SGs, and these are really nice actually. Like these are really nice dual NFETs. You can run them with like 12 volts. It just doesn't lead to any real benefits. They're mainly optimized to run on 5 volts. So that's why we see 5-volt drivers on this card, and there's also going to be a 5-volt rail hiding somewhere. Each of the FDPC's 5018 SGs obviously integrates both a low side and a high side MOSFET, so you actually have 4 MOSFETs in each phase. So if you want, like, if you just added an extra driver and another inductor, well, if you had a driver with a doubling function, you could actually run a 16-phase without increasing the number of MOSFETs. The thing is, like, putting 2 MOSFETs in one phase like this in parallel actually works perfectly fine if your main goal is to just increase efficiency, which this does a great job of, well, doing exactly that. Anyway, the noteworthy thing about the FDPC 5018SG is that it does have and that's not in my notes, so we're not going to go over it because I've forgotten what it is. Like, it has a I think it's, we'll see, 1.7 milliohms RDS on for the low side MOSFET, and the high side MOSFET is reasonably fast to switch on and off. So we're not really going to get into the details. So anyway, of that. But basically the point is, like, the lower your like the thing with VRMs is like 90% of the current going through the VRM goes through the low side MOSFET. So lower RDS on is just kind of like lower RDS on the low side MOSFET is like the easiest way to get good efficiency out of a VRM that you'd see on like a GPU or a motherboard, because they're converting like 12 volts down to 1.2 or less than 1.2 volts in the case of, you know, an RTX 20 series card. And so you really do need a very low resistance, low side MOSFET. So anyway, the combination of the 2 FDPC 5018 SGs and these drivers in each phase means that for 1.2 volts output voltage, 300 kilohertz switching frequency, and of course 5 volts drive, because, well, you know, or 5 volts gate to source voltage, because these are 5-volt drivers, the card is going to have the following heat output from the VRM. So 150 amps output, which should be slightly less than what you'd see an RTX 2070 Super pulling at stock. For 150 amps output, this VRM will be producing about 14 watts of heat, which is basically nothing. So yeah, but that's kind of what you'd expect. The thing is with the 20 series, Nvidia's reference card. Well, no, with the 1080 Ti, Nvidia stopped making terrible reference PCBs. That was like the first reference Nvidia card where I was like, "Whoa, this isn't trash. That is some progress we got right there." And then since then, they've actually stepped it up even further. So with the 20 series, the reference cards are actually pretty damn good. And MSI here, like, this is very slightly more efficient than what you'd get on a reference card, because the reference card is also an 8-phase V-Core VRM, but it uses 70 amp smart power stages. And it was just slightly, like, they just don't perform quite as well as two dual NFETs in parallel, because, well, I assume, like, the thing is, for power stages, you don't get a spec for the low side MOSFET in them. But I assume if I had that spec, I think the main difference is going to be, like, these, like, two of these in parallel ultimately have a much lower RDS on for the low side than the power stages do, because on switching losses, power stages are generally going to have a huge advantage, because you don't have to worry about impedance from the gate driver to the actual gates of the MOSFETs. So so that's kind of that. But anyway, so the thing is just like, this VRM is basically on par with the reference card. Like, I should have added that to my notes. I don't really know why I didn't do that, because I do know that I did look up the reference card's VRM efficiency just so that I have some comparison points, and now I'm like, oh, but I didn't actually write them down. But it was a couple watts difference between, like, this card and the reference card. So anyway, going up to 200 amps, you're going to be looking at about 21 watts of heat output from the V-Core VRM, then going up to 250 amps. So this is going to be above stock, because obviously, like, a 2070 Super comes at around 220 watts stock power consumption. So, you know, you'd probably be looking at something around 30 watts for the memory system. I don't actually know for sure how much the memory system would pull. I'd love to get a measurement of that, but yeah, I've not had a chance to do that yet. I'm kind of I'm kind of eyeing if the power plane here wouldn't make that easy to do, but I don't think it is. 'Cause, like, no, that doesn't look easy. Like, I was hoping there'd be some bridge resistors that you could just, like, desolder and put a shunt in between and bam, and measure it yourself, but nah, that's not available. So anyway, yeah, so 200 amps, that's around what you'd be, like, that's above what you'd be pulling stock, because the card runs on about 1 volt. So that, you know, 1 volt times 200 amps, that would be 200 watts. And then it's like, well, there's also the heat produced by the VRM, and then there's, like, a fan on the card that pulls some power. And then, of course, the memory system pulls some power, and it's just like, well, it's physically not possible for the card to, for the VRM to be outputting 200 amps, and for this GPU to be a 220 watt GPU. Right, like, the V-Core VRM can't be pushing that much current. So the stock power consumption is going to be somewhere in between these two figures, and as a result, like, the VRM, if it, like, the VRM heat output at stock is just going to be really well, you know, perfect fit. Really, it's just like that's the thing, is, like, the reference cards already are, like, designed where it's like the VRM is running at, like, basically peak efficiency, and so all of the sort of better, like, this, because there are some, like, RTX 2070 Supers where it's just like they're as cheap as can be, so they're, like, chopping off phases, you know, they're basically down costed. They take a nice PCB and then they remove everything that's kind of unnecessary or costs too much to keep on there. With cards like the Gaming X, which is one of, like, the nicer cards you can get, you basically get, like, the same level of performance as the reference cards, because those are already relatively nice, and it doesn't really make sense. Like, you could make something that's more expensive, and you can make something that's cheaper, but if you just want something kind of in between those two, you end up with something that looks a lot like the reference card this time around, which is a like, well, like, for 10 series cards, that wasn't really true. Basically, anything for a 10 series card was an upgrade, except, like, with the 1080 Ti's. You could get 1080 Ti's with worse than reference PCBs. But for 20 series, well, actually for 20 series that's true, but for like 10 series, well, no, like a 1080, you couldn't really get anything worse than a 1080 reference PCB because that was as bad as it gets. Anything below that would very likely not be able to run stock. So anyway, back to this card. So basically, yeah, like the VRM here is just designed to like hit the efficiency sweet spot, and the same as like the reference card in that regard. 250 amps output, you'd be looking at about 28 watts of heat. So at this point, well, actually even at 21 watts, you might want to start paying attention to the VRM thermals because it's not going to cool itself. 14 watts, it might actually get away with. Because the heat is spread across a whole 16, MOSFETs. So, depending on like the inductors kind of act like heat sinks, the power plane acts kind of like a heat sink, right? So depending on just how good the card itself is at sinking heat, you might be able to get away with 14 watts and like no real heat, like no actual heat sink on the VRM. But from about 20 watts up, you generally start actually needing heat sinks. In just like most of the time, unless you're looking at something really stupid like 20 plus power stages or something ridiculous like that. So, yeah, basically you want to be looking at about like 1 watt per chip, right? Because if you think about it, like this is 14 watts, so this is slightly less than 1 watt per dual NFET. And then it's like if you go up to around say 160, 170, 180 amps, you'd be probably looking at around somewhere between like 15 and 18 watts. And that would be just around that 1 watt per chip figure. And that normally tends to be where chips stop being able to cool themselves. At least in my experience. Okay. And admittedly, I've not really done thermal testing on GPUs with no VRM heatsinks because that's kind of inconvenient to set up. But anyway, basically past the 200 amp mark, VRM cooling starts being like, you kind of have to do it, but it's not necessarily like 21 watts and 28 watts. That's not difficult to deal with. 300 amps output, you're going to be looking at about 37 watts of heat. Which still really shouldn't be that hard to deal with, but this is very much like requires airflow territory at this point. You're probably not gonna, well, the thing is, you can always make a bigger heat sink, okay? So it's like saying you can't do something passively is just like, that's false. It's just that doing 37 watts passively is not necessarily practical in the scheme of building a GPU, right? So that's kind of the main concern there. But anyway, like this is not hard to deal with. It's just probably not doable without either a ridiculously huge passive heatsink or, actual airflow over whatever heatsink you do have. Now, the thing is, I'm pretty sure for 300 amps current draw on a 2070, you're looking at the very least, like dry ice levels of cooling because, at ambient temperatures, 2070s don't scale with voltage. And since the thing is, one of the main sort of power consumption drivers in GPUs is actually with really any semiconductor, is more voltage. If you run more voltage, it pulls, for CPUs and GPUs, the relationship is basically a linear increase in actual current draw. And then there's a linear increase in current draw from clock speed. So, you put those two together and you get a very... you rapidly start pulling significantly more current, especially if you're in a scenario where both the clocks are higher and the voltage is higher because the temperatures are low. So yeah, dry ice cooling, like at the very least, you'd need dry ice cooling to start approaching this figure. It might very well be in like LN2 territory. Now, what's definitely in LN2 territory is like 350 amps output and 400 amps output. And this should be doable just on the basis that this is a chip roughly the same size as a GTX 1080 Ti, and GTX 1080 Ti's do this quite easily. At least, they do that quite easily. You can do 400 amps on a 1080 Ti, no problem. So anyway, 350 amps output, this VRM would be producing about 48 watts of heat, and 400 amps, you'd be looking at about 57 watts of heat. So, these are not ridiculous. Well, okay, this is actually hard to deal with, but also it's like under extreme overclocking conditions where it's like we only need to be able to sustain this kind of current output for the duration of the benchmark. So you know, the VRM cooling considerations are basically it has to not overheat for like 3 minutes, which generally isn't that hard to do, depending on, you know, how much airflow you're throwing at the PCB of the card, because you might not be bothered with actually installing any kind of proper VRM cooling in that scenario. So yeah, like honestly, like that's the thing is like this is not in MSI's top 2070 Super, but because the reference card is already so good, this right here is like, yeah, you could totally run this on LN2. You could also run the 2070 Super reference card on LN2 as well. But yeah, like there's not really any reason to like, yeah, I'm actually that there's, as far as I'm concerned, there's not really any reason to go over this over the reference card, at least from a PCB perspective. Well, actually, no. There are some minor things that MSI does that might make life easier if you're trying to push extreme overclocks, but from like a modding perspective, but from a just, you know, VRM power delivery capabilities perspective, there isn't much of a difference. Like the reference card is like 1 or 2 watts. I think up here it's like 3 watts worse, maybe, or better. I can't remember. But basically, you know, there's a small difference between the reference card and what this card right here is capable of doing. So it's like I wouldn't necessarily buy this over the reference card for the VRM, but at the same time, the VRM is definitely not bad. So yeah, make of that what you will. Moving on from the VCore VRM, which is basically just like it's good. It's just like, you know, it's not a huge upgrade over the reference card, so it's not worth celebrating as much as when you have a GPU where the reference cards are terrible and it's like, oh look, this is a card that doesn't suck. But now it's like, well, the baseline is to not suck. So, you know, now you need to go a step further than not sucking. Anyway, here's the memory VRM. So this is our VMEM. It's controlled by this lovely chip right here, which is a UP1666Q. I like this chip because there's a full public data sheet for this thing. It's super easy to mod. It's a 2-phase. Yeah, this is actually something that might be worth messing with, even if you're just on ambient, because, well, I'm not sure if Micron GDDR6 scales with voltage, but Samsung definitely does. So yeah, if you get a Samsung-based 2070, and you know, you want more memory clock speed, throwing more memory voltage at it will actually give you more memory clock speed, which is nice because like the thing about the GPU core is going from like 1.06 volts to 1.0, actually going up to like 1.2 volts will definitely significantly increase your power consumption. It will not do anything for your overall clock speed. If anything, the increase in temperature might hurt your maximum overclock. So, yeah, that's kind of the thing with like modern NVIDIA cards in general, is just like the cores don't scale with voltage. The memory chips sometimes do. But yeah, I don't know about Micron. I've not heard anything about like if these scale with voltage or not. I really wish I did. And I'd be surprised if they didn't, like at least a little bit, right? Like, anyway, so yeah, that's a 2-phase controller, and we do have a 2-phase memory VRM, right? 1 and 2 right here. Again, we have dual NFETs, but these are very different from the ones in the VCore VRM. So these are FDPC, 5018 SGs from Fairchild Semiconductor. These right here are QA 3111s from Ubix Semiconductor, which is basic. Like I want to say it's like the same company as UPI Semiconductor, except like the names are different, and one specializes on like MOSFETs and the other specializes on like controllers. And I think some other like components, there's some other component differences between them, but they share websites. And it's just like, yeah, I'm not sure about the actual relationship between them, but they look like one owns the other, or they're like the same thing with 2 different names for their different divisions. So anyway, yeah, we do have the QA 3111s. Now these, interestingly enough, have a much lower RDS on low side MOSFET than the other ones. So, you have a low side and a high side and a high side and a low side again. So we do have 4 MOSFETs in total per phase again. And yes, the RDS on these is really low. The thing is, for that low side MOSFET, the thing is, these also have an incredibly slow high side MOSFET. And that's why they're in the memory VRM and not in vCore, because, you'd think, okay, we can totally stick these in vCore. Well, no, because to switch these on and off takes forever. And as a result, their switching losses completely negate any gains from the RDS on, which is like, yeah, well, basically, I was very, very surprised when I saw the data sheet for these, because it was these are some of the slowest MOSFETs I've seen in a while. Like there's obviously high power MOSFETs for motor drive, and those are really they're far slower than anything that we'd be looking at here. You're talking like hundreds of nanoseconds to switch them on and off, whereas for VRMs you'd be looking at like tens of nanoseconds at most. But these, for as far as things I've seen in VRMs, these are slow. These are really freaking slow. And that's the main reason why MSI is using them for the memory VRM and not for vCore, because the memory VRM doesn't need to deliver anywhere near as much power as the vCore VRM does. So, having slower, more inefficient dual NFETs doesn't really matter that much here, because, well, you're not going to be pushing that much power through them anyway, so the power losses aren't going to be that great regardless, right? So anyway, and they're still not they're not really a downgrade over what you'd get on the reference card, because you just get a two-phase with, well, actually no, they are a downgrade over what you'd get on the reference card. It's just that, well, it's the memory VRM. It doesn't really matter. This still isn't going to overheat. I have zero concerns reliability wise here. It's just yeah, these are cheaper dual NFETs. And the funny thing is MSI actually, the main reason I think that they're actually bothering to use these is because MSI uses them on other products, because otherwise most of the time you would just use the same parts everywhere. So it's kind of I was really surprised when I realized, noticed that, look, there's the Ubic logo. These aren't the same Fairchild dual NFETs as the other ones, because yeah, it's like a cost saving measure here. But ultimately one that doesn't really matter. It's just kind of oh yeah, these MOSFETs are different and they're kind of worse. Actually not kind of worse, they're just straight up worse. Unless, well, you don't buy a dual NFET to just hold the low side turned on all the damn time. So that's not really a valid use case. In that case, you just buy a low, you'd buy a low RDS on, MOSFET, and single MOSFET. But yeah, anyway, so that's the memory VRM, and there's not really anything worth talking about with it other than that. Well, my main interest in the memory VRM is the volt modding capabilities and the fact that, yeah, it seems decent enough to not blow up. So anyway, that's the memory power. And now we can look at other things on the card, like the fact that MSI has 20 amp fuses on both the 6-pin and the 8-pin, because it turns out that these two power connectors can deliver very similar amounts of power, which I've forgotten what that exact figure is right now. But the basic gist of it is this is 3 12-volt lines, and this is also 3 12-volt lines. The main difference is that this has 2 grounds and this has 3 grounds. But the thing is, unless you're running, the interesting thing about GPU ground is actually, if you measure the current, if in a normal system, if you measure the current returning from the GPU through the ground wires to the PSU, it's really low. It's way lower than what's actually going into the GPU through the 12-volt wires, because half of this connector down here is ground. And the end result is that in a lot of scenarios, a good chunk of your the current returning back to the PSU, instead of going to the VRM and then back through the 6-pin, it'll go to the VRM and then down through the PCIe slot. So if you actually want to, and I actually ended up confirming that, because I basically ran a dual PSU setup with one PSU powering the GPU, so that they wouldn't be, because otherwise the main issue is the ground of the motherboard is shared through the PSU with the ground of the GPU. Well, it's all one ground basically, between the power supply, the motherboard, and everything. And if you use 2 separate power supplies, well, then you have one ground that's for well, it's not really a separate ground, but it basically forces the current to return to one PSU instead of through whichever random path it can find to the first one. right? I really didn't explain that well. But anyway, the point is, under most circumstances, your 6-pin probably isn't isn't going to max out the capacity of its ground pins anyway. Even though it has less of them, it's probably not going to max them out. And MSI does have 20 amp fuses on here, and I'm not sure how effective these would be at actually preventing... Well, no, I can see one benefit to them. So a really common sort of failure mode for VRMs is your high side MOSFET blows up. And when that happens, it tends to blow up and fail close. Well, it depends how much it blows up. If it fails quietly, it'll probably just fail closed. If it fails violently, it probably failed closed for long enough to blow itself to pieces. And the thing is when it fails closed, it outputs, well, it basically, you run the risk of the output voltage rising to, say, 2 volts. And the thing is, 2 volts to a GPU core is pretty much instantly lethal. Like, you can, the exposure time for 2 volts to kill a GPU core might be a couple milliseconds, if not a couple microseconds. So basically, if your high side MOSFET fails closed, there's a good chance it's going to take the core with it. Now, the thing is, if you don't have a fuse like this, if you're lucky, your fuse is going to blow up before the output of the VRM rises too high, which would be great. That would be sort of the ideal solution. But the issue that you can sometimes run into with cards is cards where the high side MOSFET fails and then the PSU actually shuts down quickly enough. If you power cycle those cards with the shorted high side MOSFET still there, it's just going to jam 12 volts to the output again. So every time you try to power cycle a card where the VRM has failed, you're basically causing more and more damage, because if that initial failure didn't kill the core, every time you power cycle it, you're getting one step closer to killing it for good. So, in that kind of a scenario, the fuse can actually be helpful. I have doubts about this actually opening quickly enough to prevent the whole, to prevent a rapid increase in output voltage, but it really depends, right? That's really hard to judge. And definitely more input protection never hurt anybody. So, it's not a bad thing to have the fuses. It's just I have my doubts about how effective they would actually be at stopping much of anything, except the scenario where somebody tries to power cycle a dead card over and over again thinking that it'll magically come back. It does help in that scenario a lot. But anyway, so we do have some input fuses for the 8 pins and the 6 pins, and then we have a 10 amp fuse here for the PCIe slot, which of course is over here. So yeah, that's protected. Then we have our shunt resistors, like the main ones, so those are all the 5 milliohms. Then if we go on the back of the card, here we can actually notice that we have no current balancing circuitry. As you can clearly see, so on a lot, actually, it's been I'm not sure when exactly NVIDIA started doing all the current balancing stuff, but basically there's on modern NVIDIA cards, normally you have a whole bunch of MOSFETs for switching where 12 volts comes from and where it goes. And the idea behind this is that if you, pull too much power from, say, the 6 pin and bounce off the power limit of the card in software, it'll shove, it'll basically reconnect a phase or maybe 2 phases from the VRM to the 8 pin so that you stop bouncing off the 6 pin's power limit. Now, MSI doesn't have any of that, so I'm assuming that they've just set their per power connector power limit so high that it's not a concern, which I'm totally a fan of. In my opinion, that's the best way to solve this. Why bother with power balancing when you could just not, cause the issue in the first place? But anyway, so yeah, all of that is missing, and here we do have 2 more shunt resistors, which I believe normally are these are primarily there for, the current balancing functionality, but we can also see that this chip right over here is missing, and I think that would have been another one of these. Yeah, probably would have been another one of those. Maybe something else though. Actually, how many pins is that? 2, 3, 4. 1, 2, 3, 4. Yeah, that's the same number of pins, so I was right. It could be another one of those. So anyway, what is one of those? That's an NCP 45491. And that is the replacement of the INA 3221 that NVIDIA cards used to use. Though it looks like MSI almost put an INA 3221 right there. There'd be your capacitors for each of the 12 volt inputs. But anyway, yeah, NCP 45491. This can monitor up to 4 shunt resistors. Obviously, this card has 5 of them, right? There's 3 on the front, 2 on the back here. So I think these might not be actively monitored at all, which would make sense considering that there's no current balancing circuitry. So what's the point of monitoring which, like, the idea behind these would be like monitoring which phase is pulling how much power. Well, what's the point of doing that if you can't change where that phase is pulling the power from anyway, right? Like, doesn't actually achieve anything to be able to measure, oh yeah, phase 2 is pulling 10 amp or 20 watts. Can't really do anything about it. Like, you can't use that information to do anything, so you don't need it. Which is why I'm that's my main theory for why this is also missing. Is just like, well, there's no current balancing. It's all just resistors to handle it. So yeah. So that could potentially translate into much easier power modding on this card. At least that's my theory. Like, it might be easier to remove the power limit on this. Because basically, like, as I was very late to realize, the thing that really screwed me over when I last tried to work on a 2080 Ti was all of the current balancing circuitry. Because it obviously has its own monitoring system. So it's like, if you override the primary, measuring methods, you still haven't overridden everything downstream from there. So the card still knows how much power it's actually pulling, and it'll still do its freaking power management stuff. Anyway, so yeah, I just kind of find that interesting. And this is not the only card MSI has where they've just kind of removed all the current balancing circuitry. So yeah, I think it's kind of neat that their cards don't have it. Because honestly, like, my personal opinion on the current balancing circuitry is that it's an unnecessary solution to a problem NVIDIA created. You don't see this kind of stuff on AMD cards because, well, AMD cards just don't have per power connector limits. It's just not a thing. It's just like, well, I guess we're pulling this much power from the, in some cases it actually causes potential issues like the RX 480, where it was like, well, I guess we're pulling a little bit more than spec from the PCIe slot, which in my opinion is like not an issue, but there was a whole lot of controversy over that, so it's just like, but whatever. So I think that's kind of neat. Some people might disagree with that, but whatever. There's no current balancing circuitry on here, and I assume like MSI just has a really high power limit on this card to basically get around that. What else did I want to talk about? Oh well, just because I have a great interest in all like capacitors, right? We can see for the memory power plane, we have some SMD polymers that are like, so obviously like the memory VRM's right here, and we have the bulk of the capacitors, the bulk of the bulk capacitance right on the output of the VRM, right, which is pretty normal. But for the far away memory chips, like if this memory chip or this memory chip or this memory chip suddenly needs a lot of current, it can actually grab that current from the capacitor right next to it instead of having to like reach across the entire bloody power plane to get it from the memory VRM and this capacitor bank right there. So yeah, and it's just kind of like I guess this works. It's basically my observation. Is just like It's just like, yeah, the MSI is doing this on the memory power plane. Though the thing is, like, I've not checked if other cards are doing this, so I'm not sure if this is like a requirement or if MSI is just doing this out for like memory overclocking improvements. Because, yeah, in theory, like, the main benefit to this would be that you could clock the memory. Like, if this is different from what you'd see on a reference card, then the main gain would be, like, in theory, you might be able to clock the memory a bit higher. Though, judging by the review of this card, that doesn't seem to be the case. So, anyway, and then for the VCore VRM, so this is one interesting thing is, like, the reference cards from NVIDIA are all, you know, surface mount capacitors for the bulk capacitance of the VCore. Now, MSI has obviously opted for a bunch of through-hole capacitors, as we can clearly see the legs right here for those. And so to basically, and the thing is with the surface mount capacitors, they offer superior ESR, at least most of the time, and superior ESL, which is like the main difference is like the ESL advantage for the surface mount capacitors is kind of massive because you can actually get like 5 milliohm ESR through holes. It's not that hard, but getting through hole caps with as low an ESR as your surface mount ones, that's basically impossible because of actually not basically impossible, literally impossible unless you're looking at a garbage surface mount capacitor. Because basically the way these are packaged, like that packaging inherently has more equivalent series inductance. So the end result is that these are basically worse at dealing with high frequency transients. So that's why you can see, like on a reference card, you just have a bunch of surface mount capacitors and then you wouldn't really have anything else. But MSI, because they opted for a bunch of through holes, you still see the surface mounts kind of jammed right up against where the GPU core is, right? Because that, like, get back the orange. Like you can see the V-core power plane going up to the GPU core right here. And so these are there for the GPU core. Those aren't on memory power. This one is, because you can see that, this end is on the actual memory power plane. So anyway, yeah, that's just kind of interesting observations. And if you're wondering about like, well, why doesn't MSI just use a bunch of surface mount capacitors on the output of their VRM instead of a bunch of through holes? The surface mount capacitors are significantly more expensive. So yeah, that's why you see them on like the memory VRM where, they might actually have some pretty major advantages there. I guess it might also be a like heatsink clearance thing here where it's like, oh, there's, mounting holes all around. So it's just like, well, we want to clear the heatsink. But here, like MSI's given themselves plenty of space, right? Like on a reference card, the capacitor bank is jammed right up against like it would basically be right here. My orange is all ugly. It would basically be right here. But MSI's basically shifted the entire V-Core VRM back a bit so that they can accommodate their heatsink. And then it's like, yeah, just use the through-hole ones because those are cheaper. And then add a bunch of multi-layer ceramics in front of them to try, again, like to basically work around some of the like basically the lower ESL, like it's not lower, higher ESL that these come with is just like compensate for it with a bunch of multi-layer ceramics. So yeah, ultimately this is like a difference. You'd actually have to take an oscilloscope to the card to measure if MSI's approach is better. It might be, or if NVIDIA's approach is better, because ultimately this I do believe ends up with significantly more actual total capacitance on the output. But it's just like, yeah, if you're like having a lot of capacitance that sits behind a bunch of ESR and ESL is actually kind of useless because your really fast transients will just not use won't really make much use of the extra capacitance that you've added. Is basically like that's the really simplified version of that. So yeah, anyway, that's kind of it for the 2070 Super Gaming X PCB. It's a 2070 Super. It's about on like it's an alternative design to the reference card. It's not really any. It's not better in any obvious way. It's not worse in any obvious way either. Though MSI has added they've added the fuses, which are just like you don't have fuses on the reference cards. And they've eliminated the current balancing circuitry, which I'm a fan of, but some people might not be. Other than that, it's just like efficient, like VRM efficiency wise, you're looking at pretty much the same results as a reference card. But obviously, like the thing is this comes with a better heatsink, right? Like that's the primary thing with this card is like this comes with a better cooling system. And it also comes with a perfectly good PCB. So yeah, that is it for this video. So thanks for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. And if you'd like to support what I do here with actually hardcore overclocking, I do have a Patreon where you can support me directly through a link down in the description below. Or if you'd like to buy some AHOC like merch, so shirts, stickers, posters, socks, you can find a link to Teespring down in the description below and find all of that there. And one last time, thank you to Tech Power Up for providing high-res PCB pictures like this in their reviews. There will be a link to their review of the RTX 2070 Super down in the description below. And they do actually like cover things like VRM thermals and gaming performance and, you know, the things I don't do because, well, I don't have the card in hand. And actually, I wouldn't cover gaming performance if I had the card in hand because we all know my favorite game is 3D Mark. So anyway, that's it for the video. Thanks for watching and goodbye.